Hi everyone, I am S. Vidyarani, working as Assistant Professor of Physics at MVS Government Degree College, Autonomous, Mehboob. Today we will be going to discuss about some theorems which are very useful and which are very known theorems that we use in vector analysis. Those are called as Stokes as well as Gauss Divergence Theorem and Green's Theorem. In today's session, we will be discussing about Stokes theorem as well as Gauss divergence theorem using examples. First, let us see what is Stokes theorem. By the definition of Stokes theorem, it states that the circulation of a vector field A around a closed path L is equal to the surface integral of curl of A over the open surface S bounded by L, provided A and curl A are continuous on S. In other words, in mathematical form, this can be expressed as line integral of any vector, say A dot dl, is equal to surface integral of curl of A, which can be represented as del cross A into ds, which resembles the surface area. Okay, so here if you see in Stokes theorem as from the definition, so let us say a vector field A is around a closed path L. So this is equal to the surface integral of that curl of A, which is bounded by that L, and whereas A and curl A should be continuous on S. So from the statement of Stokes theorem, let S be an open surface bounded by a closed curve C and vector F be any vector point function having continuous first order partial derivatives. Then this can also be represented as F dot dr, where this is line integral, and whereas this is surface integral, which is represented by two integrals, surface. So curl F dot n ds, which means curl F and n is the unit vector. So curl F is nothing but del cross F. Whereas here we have shown in the position vector, hence we have taken unit vector, where n is equal to unit normal vector at any point of S drawn in the sense in which a right-handed screw would advance when rotated in the sense of the description of S. Stokes theorem also relates a surface integral over a surface S to a line integral around the boundary curve of S. When you see the mathematical form, that means line integral of any vector can be expressed in terms of surface integral by using curl. So this is the relation between curl as well as line integral. So line integral can be changed, line integral of any vector can be changed into surface integral using curl or cross product. Let's see with an example. Let us evaluate line integral of f dot dr, where f is a function of x, y, z, and it is given in its components form minus y square I plus xj plus z square k. Let's see is the curve of intersection of the plane y plus z is equal to 2 and the cylinder x square plus y square is equal to 1. Orient C to be counterclockwise when viewed from above. This is the condition and these are the parameters that has given in this example. Based on these parameters, we will build up a curve as well as a cylinder. Let's see. So there's a curve C. This is the curve C, which is filled with blue color. This is the curve C. So the curve C or an ellipse is shown here. So this is the construction of the given parameters. So curve C, the equation is y plus z is equal to 2. So these are all the three axes in all the three directions, x, y and z. O is the origin. So this is d is the diameter, s is the surface area covered by the curve C. First let us compute. In order to change line integral into surface integral, we will require curl f value, that means del cross f. So using the values of the given equation, we will first compute what is del cross f, or cross product of del and f. So we know that curl f is nothing but taking the determinant of the given vectors. So I, j, k are the unit vectors. So del has dou by dou x as well as dou by dou y and dou by dou z in all the three unit vectors, are in all the three directions. And f is a function of, we have given that f is a function of minus y square I plus xj plus z square k, where is minus y square is the magnitude in respect to I, whereas x is the magnitude with respect to j, z square is the magnitude with respect to k in the z direction. So taking all these three values, we have taken here minus y square, x and z square. So when we take the determinant, see, when we are taking the determinant, what happens? I into dou z square by dou y, as it's a partial derivative, there is no y term, hence dou z square by dou y value becomes 0, minus in the same way dou x by dou z. Same way we have to take the partial derivative with respect to z, but there is no z term, hence dou x by dou z also becomes 0. That means on the whole the component of I becomes 0. In the same way minus j, we have to consider the second component minus j, and taking the derivative dou z square by dou x, again there is we have to take the partial derivative with respect to x, but there is no x value, hence dou z square by dou x becomes 0, and minus dou y minus of dou by dou z of minus y square becomes plus dou y square by dou z. Again we have to take the derivative, partial derivative with respect to z, but there is no z term, hence dou y square by dou z also becomes 0. That means on the whole jth component also becomes 0. But when we move on to the kth component, that is third component, here the determinant is as follows: dou x by dou x. So we have to take partial derivative with respect to x. There is x term in the numerator which we have to take the partial derivative. Hence dou x by dou x becomes value 1. Hence I have taken the value of 1 here. Next minus of dou into dou by dou y of minus y square. So minus of minus becomes plus, and we have to take the partial derivative with respect to y of y square. So we get 2y as our partial derivative. Hence we got 2y here. So this is with respect to kth component or kth unit vector. Hence 1 plus 2y into k. I, j components values become 0, but whereas kth component value we got it as 1 plus 2y into k. This is the value of curl f. So the elliptical region S in the plane y plus z is equal to 2 is bounded by the curve C. So if you orient S upwards, C has the induced positive orientation. So when we move S upwards, what happens? The C will be having positive orientation. So the projection D of S on the xy plane is the disk x square plus y square is greater than or equal to 1. So this is the condition that we have to apply. So for this condition to be applied, we have to consider from Stokes theorem, line integral of f dot dr is equal to surface integral of curl f into ds. So here we have to take the values of d, hence integral d, curl f value is 1 plus 2y, hence into dA. Next, if you consider the values of dA, so it can be written as 0 to 2 pi integral and again integral 0 to 1. So the value of curl f is 1 plus 2y. Y can be written as r sin theta in terms of r and theta values, and dA can be written as r dr d theta. So when we take the inner integral with respect to dr, so the integral value we will get it as 1 into r is r, so integral of r is r square by 2, as well as plus 2r sine theta. So 2 sine theta is constant value. We have to differentiate r square. So we will get it as r cube by 3 into sine theta within the limits from 0 to 1 into d theta. So again integral 0 to 2 pi, when we substitute the values of upper limit and lower limit, so our values will be 1 by 2 plus 2 by 3 sine theta for the upper limit value 1 into d theta. Again if we take the integral of this whole value, so we get 1 by 2 into, we get theta here. So theta means again upper limit we have to apply and lower limit we have to apply. Theta for upper limit is 2 pi, hence 1 by 2 pi, plus if you see here 2 by 3 sine theta d theta. When we take the integral for this value, we know that sine theta value for 2 pi, that means 360 degrees, will be 0. Hence we get a 0 over here. As well as when we apply lower limit also, so sine 0 is also a 0 value. Hence this second value term becomes 0 when we apply both the upper limit and the lower limit. Hence for the second term the value is 0. Then if we simplify further, 2 gets cancelled over here. So the total value, final value, we get it as pi. So this is how we will be solving or will be using line integral and changing it into to find out the surface integral. Also we will see one more example. Using Stokes theorem, we will compute curl f dot ds, where f of xyz is a function xzi plus yzj plus xyk. Let us say S is the part of the sphere equation x square plus y square plus z square is equal to 4 that lies inside the cylinder x square plus y square is equal to 1 and above the xy plane. So taking all these parameters into consideration, when we draw a figure, so the figure will be like this. If you see here, the sphere is this. So the sphere has the equation x square plus y square plus z square is equal to 4. In that one cylinder is embedded. That cylinder equation is x square plus y square is equal to 1. So it is in the xy plane. So we have taken all the conditions into consideration. Now we have to find out this area, surface area of this value, which is shown in blue color. So to find the boundary curve, let us say C. First we have to solve both the equations. So the equations which we got, x square plus y square plus z square is equal to 4 and x square plus y square is equal to 1. So when we subtract these two equations, so x square y square and x square and y square in both the equations gets cancelled. So the remaining value will be z square is equal to 4 minus 1, that is z square is equal to 3. On subtracting we get z square value as 3. So the value of z will be on the root 3 since z is greater than 0. So C is the circle given by, now we have the circle equation x square plus y square is equal to 1. This is the previous equation that we got from the question, and now we have found out the value of z, that is equal to root over 3. So this is the circle, C is the circle given by the equations of these values. Now, a vector equation of C can be written in this way: R of t is equal to cos ti plus sin tj plus root 3k. So this is the where t lies between 0 and 2 pi. So these are the boundary conditions. Therefore, when we differentiate r, so it becomes r dash t, and the derivative of cos theta becomes minus sin t. So hence minus sin ti plus, so again sin t derivative becomes cos t. So cos t into j plus, this is a constant value. We cannot take the derivative. So its value is 0. Hence there won't be any kth component or kth parameter. Therefore, this is the equation that we got after differentiating the r of t. Now we have equation here. If you see the previous question, here f of xyz is given as x into z into I So hence we have to consider the value of x, the value of z for the ith value. Hence what we have to do, here x value is, here if you see the three components, this is x value, xi plus yj plus zk. So we want x comma z value. So x into z into I. So x is cos t, z is root 3. So root 3 into cos t. So x z into I. This is from the equation of function f that is given here. X into z into I. So next plus y into z into j. So y into z into j, taking the values of y and z from this equation. Y value is sin t, z value is root 3. So yzj value becomes root 3 sin t j. Plus in the same way for the third term, if you observe, it is xyk. So from this equation, what is x? Our x is cos t, our z is root 3. So we want xzk. So x is cos t, z is root 3. Hence xz will become, xy will become cos t sin t into k, because we have to take xyk. So these are the three values when we take the function with respect to the vector equation r of t. So now we have f of r of t, we have r dash t. Now using these two equations we will find out the value. So thus by Stokes theorem we know that surface integral of curl of f ds is equal to line integral of f dot dr. Okay, so we have to apply the limits. Remember this 0 to 2 pi. Hence I have taken 0 to 2 pi within the integral f of r of t in dot r dash t, where dr can be written in terms of dt using r of t dot r dash t. F of r of t that we got from the above equation is minus 3 cos t sin t, whereas if you see here f of r of t is this value, r dash t value is this value. When we do the dot product between these two, only I dot I becomes 1, j dot j becomes 1. So eliminating this term, we get minus root 3 sin t cos t plus root 3 sin t cos t. So that is the equation we got here. See, minus root 3 cos t sin t plus root 3 sin t cos t dt. So both are one and the same. This is also root 3 cos t sin t, this is also root 3 cos t sin t, but with a different symbol, that is one is plus, one is minus. So both gets cancelled. So remain, all this value becomes 0, because this is plus value, this is minus value. So both are equal, hence plus minus becomes 0. So we got here the value as 0. 0 to dt within the limits or within integral 0 to 2 pi. So integration of 0 is 0. Hence all root 3 into 0 also becomes 0. Finally we got curl f dot ds value as 0. This is how using line integral we can find out the surface integral of any surface using Stokes theorem. That means Stokes theorem can be helpful for any vector which is expressed in terms of line integral that can be changed into surface integral using curl. Now we will move on to Gauss Divergence Theorem. Gauss Divergence Theorem, from the definition, the divergence theorem states that the total outward flux of a vector field A through the closed surface S is same as the volume integral of the divergence of A. If you observe this is given by surface integral A dot ds can be written in terms of divergence of that vector A enclosed in the volume dV. Hence this can be written as surface integral of A dot ds is equal to volume integral of div A into dV. So from the definition of divergence of a vector field, we know that the divergence of a vector field at a point is always a scalar quantity. We have already discussed in earlier classes, divergence of any vector field is a scalar quantity of magnitude equal to flux of that vector field diverging out per unit volume through that point. In mathematical form, the dot product of del operator and the vector field A gives the divergence of a vector field A. So div A can be written in terms of del dot A, which produces a scalar quantity. So we can also say that this is the divergence of A, or dot product of del and A is scalar. But we know that del value is given by I dou by dou x plus j dou by dou y plus k dou by dou z, and A is equal to, in terms of all the three components, axi plus ayj plus azk. So when we perform dot product between these two vectors, del dot A gives rise to, we know that from the properties of vectors, so we know that in divergence when doing dot product, so I dot I becomes 1, j dot j becomes 1, k dot k becomes 1, and all other combinations becomes 0. Hence we are applying the same here and finding out I dot I value as 1. Hence dou by dou x into ax, which means dou ax by dou x. In the same way, j dot j becomes 1. Hence dou into ay by dou y, that becomes dou ay by dou y, plus k dot k becomes 1 again. So dou by dou z into az becomes dou az by dou z. So this can also be written as divergent A or div A. So that is dou ax by dou x plus dou ay by dou y plus dou az by dou z. Now if you see the physical significance of divergence, the divergence of any vector field can be positive, negative or 0. As I have told just now that, so divergence of any vector field is a scalar. That scalar value will have only magnitude. So that magnitude can be positive, negative or maybe 0. Suppose if the divergence of a vector field at a point is positive, let us say divergence A is positive, it means that the flux entering through the surface is less than the flux coming out through that surface. So what it means, if divergence A is positive, that means whatever the flux entering into the surface is less than the flux coming out of the surface. That means there is a source of that vector field in the region. Second condition, if the divergence of a vector field at a point is negative, that means the flux entering through the surface is more than the flux coming out through that surface. That means here, in other words, there is sink of that vector field in the region. If divergence A is positive, so there is a source vector field, whereas if divergence A is negative, that means sink of that vector field is present in that region. Suppose if the divergence of a vector field is 0, it implies that the flux entering into the surface is equal to the flux leaving that surface. So whatever the flux entering into the surface is leaving from that surface, hence there is no divergence. Hence, in other words, there is neither sink nor source in that region. Gauss Divergence Theorem. Using this, the above divergence theorem, we formulate a theorem called Gauss Divergence Theorem. According to this theorem, the volume integral of divergence of a vector field A over a volume V is equal to the surface integral of that vector field A taken over the surface S, which encloses that volume. Just now I have told. So any surface integral of any vector can be expressed in volume integral using divergence. So hence the name given Gauss Divergence Theorem. Thus this theorem is used to convert the volume integral into surface integral or vice versa. That means surface integral can be converted into volume integral. In both the ways, this Gauss Divergence Theorem helps us to change surface integral into volume integral or volume integral into surface integral using this condition. Let us see the proof. for this Gauss divergence theorem. In Cartesian coordinates, we know that divergence A, that means dot product. So del dot A is equal to I dou by dou x plus j dou by dou y plus k dou by dou z dot I ax plus j ay plus az k. So just now I have told how to do the dot product. So using the dot product, we got the values of dou ax by dou x plus dou ay by dou y plus dou az by dou z. And we know that the volume enclosed by the value is equal to, by the body is dv. So dv can be expressed in all the three directions using dx, dy and dz. We know that while a dot dA is the surface integral. So we know that a is axi plus ayj plus azk vector. dA is given by I dAx plus j day plus k dz. Again doing the dot product. So I dot I values becomes 1, j dot j value becomes 1 and k dot k values becomes 1. Only 3 values will be existing. So hence when we see this, I dot I becomes 1, hence the value coefficient of I is ax. Here the coefficient of second I value is dx. So ax into dax. So that we got over here. Again j dot j. So jth term here. So j dot j becomes 1. Again ay into day. So that I have written here ay into day. Same in the case of the third term. K dot k is equal to 1. So k coefficient is az. Here k coefficient is daz. So az into daz will be multiplied. So az daz. So this is the equation that we got here. So ax dx plus ay dy and az dz. This is the way we express here. So if you see here a small mistake has been done by me. So if you see here, this dAx can be expressed in terms of dy dz. dy can be expressed in terms of dx and dz, whereas dz can be expressed in terms of dx and dy. Hence, substituting all these values, we get, so according to Gauss theorem, so left hand side we have volume integral of divergence. So dou ax by dou x, this we got from here. Divergence A is dou ax by dou x plus dou ay by dou y plus dou az by dou z. We have to take the volume integral. So I have taken 3 integrals to represent volume integral. Dou ax by dou x plus dou ay by dou y plus dou az by dou z. And dv value I have just now told. dv is equal to dx into dy into dz. So this volume integral is equal to surface integral. So to represent surface integral, I have taken 2 integrals which represents surface integral. So this surface integral of ax in terms of dy dz plus ay in terms of dx dz and az in terms of dx dy, that we got from this. So this is the surface integral value of a dot dA. So this we got here. That means we have shown any volume integral can be changed into surface integral with the help of divergence, or else surface integral can be changed into volume integral using Gauss Divergence Theorem, hence proved. Thank you for your patience listening. Signing off for today's class. Thank you one and all.